This video is about failure modes in bending members, but more particularly about the buckling failure mode. We'll start off by thinking about normal failure modes. Bending members normally have a rectangular cross-section. If we're bending it so that the bending axis is this horizontal axis, that is major axis bending. And most pieces of timber have got much better strength for major axis bending than they have for minor axis bending. So if we're bending it about a horizontal axis that's parallel to the long dimension of the timber, that's minor axis bending. So I'm now bending it by rotating my hands outwards, and we get a classic bending failure which is initiated by tension on the bottom surface of the member. The next failure mode that we're going to think about is a buckling failure mode. And if I load a piece of timber up in minor axis bending, you can see that the member is uniformly deflecting downwards, but it's not twisting to the side. If, on the other hand, I put it into major axis bending, then the buckling mode is quite different. Can you see that the top part of the member is moving to the side? That's because by putting this bending moment on the member, I'm putting compression into the top and tension into the bottom. The compression edge wants to move sideways and the tension edge doesn't want to move sideways. So that is classic lateral torsional buckling, which is what we get out of bending members. It's lateral because the top is moving sideways, and it's torsional because the middle part of the member is appearing to twist. We don't get lateral torsional buckling if we bend it about the minor axis. It's only a function of major axis bending. In considering whether or not a bending member is going to buckle, the slenderness is dictated by the ratio between the depth of the member and the width of the member, the depth to breadth ratio. So if I take a member like this, the one that I have been using already, you can see that it's relatively easy to induce a buckle into it. If I take this member, which has got a smaller depth to breadth ratio, this member here is much, much harder for me to buckle. And here is a real bending member, and you'll see that I've got no way of buckling this one. The K12 factor is its tendency to buckle, calculated by using the cross-sectional dimensions of the timber, and in particular, depth to breadth ratio. Once that's been calculated, we can then go from the slenderness to the K12 value, which is going to range from 0 to 1. For stocky members, it's close to 1, and for very slender members, it's going to be less than 1. And if it is less than 1, it's indicating that the failure mode of the member is more likely to be buckling. So for the design of bending members, it is important to calculate the slenderness of the member, then the stability factor K12, and that will be a key part of evaluating its bending capacity.